Okay, so that's fin resistance. Like I said, the most tricky thing is to realize once you've computed this, you have an expression for what's happening at the base. So let's now move into an example that's not just a rectangular fin. All right, so let's say we have an extended surface, and it's something like a washer that's maybe brazed onto a tube, and we want to be able to model the temperature, heat transfer, whatever, that's going in the radial direction in this system. So let's walk through this example. I think we'll see, we'll see what happens when you have an additional r in there. And then it'll introduce us to this set of functions called Bessel functions, which maybe if you've had heat transfer before, you've briefly seen. But it's a geometric function that's often encountered in heat transfer problems, so it's good to see those at some point. Okay, so let's just walk through this example. First thing we want to do is let's decide whether an extended surface approximation is valid here. So we would first compute the BO number. Right, the BO number is going to be the R conduction in the x direction. So I don't have coordinates here. So let's say this here is x, and this is y. Better make sure this is R, right? So we want to look at the conduction in the x direction and then compare that to convection. So R convection, or the resistance to the surroundings. So if we do that, we have what? So the conduction in x is going to be the thickness divided by 2 times conductivity times the surface area, which is going to be pi r out squared minus r in squared. Right, so that's our surface area. And again, what are we assuming here? We're assuming that our worst case scenario is heat flowing from the center line out. There would never really be a case where you'd have heat flowing from the top surface to the bottom. So we're, because of the symmetry of the problem. So we're just going to say it's going to flow thickness over 2, and then the area that it has to go through to get out is just one of the disks on top. Okay. Where are we? So the other part of this is the convective resistance. So that would be here, hopefully not run out of room. So it'll be 1 over h bar times pi times that same area, r out squared minus r in squared. Okay, so this, if you simplify it down, just becomes thickness times h bar over 2k. If we were to have actual values for this, like conductivity and radius and stuff, we could compute this. But let's just assume for now that it checks out. Our BO number is less than 0.1 or some small number, and we're set to go. I'm going to move this over slightly, so I need room on this side here. Okay, so we're check on that. Let's say that checks out. Now let's go through actually deriving the ODE and solving the problem. So down here I've already drawn it out, but we have our energy balance here, or our control volume analysis. We have heat flow coming in the R direction, leaving in the R direction, and then we have convection to the surroundings. Be careful again that if, depending on what we assume, we're going to want to probably use the total area here. But we need to be consistent about the area that's exposed for convection. So let's write out expressions here. First, our energy balance is as follows. We have, skipping the actual energy balance, expanding out, we end up with 0 equals d q dot dr times dr plus q dot convection. Right, that's just expanding out that qr plus dr term and canceling it out. For heat transfer q dot is going to be minus k 2 pi r thickness times dt dr, and convection is going to be 4 pi r dr times h bar times t minus t infinity. Right? So that 4 pi, or 4 is the top and the bottom surface. So it'd normally be 2 pi r dr, but we have both top and bottom. So we can take that, substitute it in to our equation above, and we end up with 0 is equal to d dr of minus 2 pi k r thickness dt dr times dr is equal to, oops, sorry, it's just plus 4 pi r dr h bar t minus t infinity. Okay. A few things can cancel out the constants. 2 pi can cancel out. One of the drs can cancel out. And we have then a simplified equation written in standard form, which would be something like the following. d dr of r dt dr minus 2h bar over k thickness times r times t is equal to minus 2h bar over k thickness times r t infinity. Sorry, this is separate these out. Right, so there's our governing ordinary differential equation in temperature. A few things again to observe, as with most fin problems or extended surface problems, this is a non-homogeneous equation. On the left hand, we have all of our stuff with temperature, and on the right hand, we have some function of the independent variable. So yeah, we need to go through this process of particular solution and homogeneous solution again. At this point, if you wanted to, you could, I think it's worth it to do this by hand a few times to understand what it is like. And then you could plug it into Maple and get the solution. In the future, though, by the way, there are situations where like you might plug in some non-homogeneous ODE or PDE, and Maple just won't solve it. But if you were to break it up yourself and do a homogeneous solution and then a particular solution, it would solve it. Right, so you might still have to use your own knowledge or judgment as you're going through the process just to get it to do what you want. Okay, but there's our ODE. Let's make that substitution where we say T is equal to TH plus TP. So the first thing would be, let's rewrite this. Let's rewrite this in terms of our particular solution first. Particular solution. Okay, so this is d dr r dt p dr minus 2 h bar over k times thickness r tp equals minus 2 h bar over k thickness r t infinity. Okay, remember what we have to do for the particular solution. We need some function that when we do the operations shown here, gives us back the right-hand side. So with the example we had last time, you can almost just sit here and look at this and know what TP is going to be, right? So stare at it for a second. First of all, if we guess TP is equal to a constant, this term goes away. We have then this term, which also appears over here exactly, saying my constant is equal to T infinity, right? So by inspection and with some experience, you can sit there and see that. If you didn't see that right away, you would follow the rules that we said before. And that means I would need to guess some function that is the right-hand side times a constant, or whatever appears on the right-hand side. And then the derivative of that times another constant, and the derivative of that, and so on. So what we would guess here would be TP is equal to C, let's say C3, just because we're going to need to save 1 and 2 for the homogeneous solution. So C3 times, what's on the right-hand side? Well, it's a bunch of constants times R. So I would guess C3 times R. And then the derivative of that, which would be plus C4, right? And the derivative of that, which would be 0. So then I'm done. So now if I take that function, sub it in, go through the process, you're going to end up finding, again, that TP is equal to T infinity. And that's your particular solution.